Hello and welcome to the Scientific Adventures of Beardman. Today we're going to be talking about a concept builder. That did not work right. A concept builder on the physicsclassroom.com under the topic of waves and sound. Title is Name That Harmonic Closed End Air Column. This is the third in a series of Name That Harmonic. The first one was Name That Harmonic Strings, and I'd recommend if this goes too fast to go back and take a look at that. I'll link that here. So first, for the apprentice level, let's just review what harmonics are. So remember, waves bounce back and forth. The air, a flute would be an open air thing. This would be like, I always think of the Country Bear Jamboree at Disneyland, where the bear's blowing on the jug. The bottom of the jug is closed, and so the top is open. So one side's closed and one side's open. That's our situation here in a closed end. Only one end is closed. Some people estimate your voice as a closed end because the bottom of the lungs is closed, but the top is open to the air. But there's, Anyways, so those are some possible examples, some examples. So as those waves bounce back and forth between the open and in the closed end, there's spots where they will destructively or constructively interfere, and those are called antinodes, and other places where they'll destructively interfere are called nodes. Only certain frequencies match up just right as they bounce back and forth, and those particular frequencies are called harmonics. The lowest level harmonic is the first harmonic. Because one end is closed, we get an antinode there. Where it's open, we get an antinode like this. Where it's closed, we get a node like this. And so our first one is actually just a quarter of a wavelength. Our other two types of harmonics involved half wavelengths. This is a quarter of wavelength. One side always has to be at a node, and one side has to be at an antinode. So the next time that happens is not when it's twice as the frequency is twice as big, but when it's 3 times as big. In other words, 3/4 of a wavelength. We have a closed end here and an open end here. So we have no second harmonic because the second harmonic would have to end like this, and then we'd have a node at both ends. That can't happen because one side is open and one side is closed. So we have a first harmonic, a third harmonic, a fifth harmonic, a seventh harmonic, because all of those have that extra quarter wavelength that allows us to have an antinode at one side and a node at the other side. I find the easiest way to count these is by looking at what's in the middle. So in the middle, we're partway between the equilibrium and the crest, the maximum. And so if you count those, you can count quarter wavelengths if you prefer, but I just go through, here's a quarter wavelength, that's 1. Here's a quarter wavelength, that's 2. Here's a quarter wavelength, that's 3. So if you just kind of draw a line across halfway up here, the number you pass, 1, 2, 3, that's the third harmonic. Let's put that into practice here. So here, remember, a quarter of wavelength is a harmonic. So if we want to look at for actual quarter of wavelengths, that lets us count it. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so this is the 13th harmonic. I'll just put H. If we want to draw a line across here, like I'd mentioned earlier, we can put in some numbers: 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 10, 11, 12, 13. Okay, so that lets you count it. So there are 13 quarter wavelengths, and a quarter wavelength is the lowest wavelength, the fundamental frequency. And so there are 13 quarters, so it's the 13th harmonic. All right, so frequencies, same idea. Our fundamental frequency is here. Multiply that times the number of the harmonic, third harmonic, fifth harmonic, etc. Notice we'll only have odd numbers of harmonics, and that'll give us the frequency of that harmonic. So our sample problem here, we see the fundamental or first harmonic frequency of closed air tube is 90. Okay, so F1 equals 90 hertz. And we see that the same air column is capable of vibrating with several different other standing wave patterns. Identify the standing wave pattern for the harmonic that has a frequency of 630 hertz. So Fn equals 630 hertz. Okay, so we know that Fn equals n times F1. We rearrange that dividing both sides by F1 like we did in the other videos. We get Fn over F1. We plug in our numbers, 630 hertz divided by 90 hertz. And 630 divided by 90 is 7. So this is going to be the seventh harmonic. Seventh harmonic. We've got 1, 2, 3, 4, 5, 6, 7. Okay, if we want to draw our equilibrium in there, and then we could draw our alternating halves of the wave where it's flipping back and forth between, and we see we've got a node at one side and an antinode at the other with 7 quarter wavelengths, or you could imagine going along a line here and you're going to cross 7 times. 1, 2, 3, 4, 5, 6, 7. All right, and that's the master level. Moving on to the wavelength, the wizard level, we see that we have a change here because we no longer have our fundamental frequency being half a wavelength, it's a quarter wavelength. We've changed this from a 2 to a 4. Since it's no longer half, it's now 1/4 the wavelength. The length would be 4 times longer. The wavelength is 4 times longer than the length for the first one, so we need a 4 there. All right, moving on to the wavelength. Once again, if any of this is going too fast, go back to the name that harmonic for strings, and everything goes much slower and clearer. Here I'm assuming you know all that. So here we have a closed-end air column that has a length of 44 centimeters. So that's the length of the air column. Identify the standing wave pattern for the harmonic. Has a wavelength of 16 centimeters. 16, that's the wavelength. And so we have wavelength equals 4 times L over N. Solving for N, we get N equals 4L over lambda. We plug in our values, 4 times 44 centimeters divided by 16 centimeters. Centimeters cancel, and we get 11. Okay. So if we have the 11th harmonic, it means we're going to need 11 quarter wavelengths. And so that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Our equilibrium in here. If we put our alternating side, it would look like this. And that is what our wavelength, the wave setup would be inside of this closed air column. All right, enjoy blowing on your bottle, the Country Bear Jamboree. Anyways, doing some calculations here, and click that like and subscribe button. If you have any questions, please leave a question in the comments. I'd love to answer that for you. And we'll see you the next time on the scientific adventures of Beardman.